Andrew Ninka, and I'm going to be talking about split-slice training augmentation for RAKI networks. I have the shown conflicts of interest. Recently, deep neural networks have been proposed to effectively replace the linear graphic kernel with a convolutional neural network. Here's a RAKI network. It's designed to be trained uniquely for each slice and coil for each imaging exam, just as graphic kernels are uniquely fit for each exam. This neural network is shallow compared to other solutions so that it can be trained rapidly. The input includes a real-valued representation of the acquired complex-valued multi-channel data with real and imaginary observations for each coil included as unique input layers. The output is the desired complex-valued k-space for the coil and slice. Table shows a number of hyperparameters for the RAKI network which were considered through an exhaustive grid search in our experiments. Here we introduce ideas from SplitSlice graph into the RAKI deep learning reconstruction technique. The SplitSlice formalism essentially yields a form of training data augmentation for RAKI. The network ingests aliased k-space data and outputs the desired unaliased data. Standard RAKI training is depicted with the first row of this figure. With split-slice augmentation, individual slice data are summed across a subset of the slices in the acquired packet. The full set of to-the-end training datasets includes some combinations in which the slice to be reconstructed is not included in the input, and those sets are paired with an array of zeros as the desired output. While RAKI training is done with a single alias dataset paired with the desired unaliased k-space, split-slice formalism yields 256 training sets for an 8-band acceleration factor. Here's what we found. Split-slice training augmentation generally yields improved performance compared to standard training except when dropout is used. This suggests that overfitting can be a key concern with RAKI networks, which can be addressed by including dropout layers or by training data augmentation with the split-slice formalism. Optimal networks are shown on this slide. Differences in training yield significant differences in optimal network hyperparameters. While this work uses this de facto standard HCP acquisition, it is expected that network hyperparameters should be individually considered for studies using other acquisition techniques. Thank you for listening to my presentation. Check out more details in the links below.